Hello, welcome to this video produced as part of the Further Maths Support Programme's material for A-Level Maths and Further Maths. This one focuses on the basic principles of work, energy and power. It's section 2 and we're going to look this time at power, force and velocity. Our basic definition of power was work done over time taken. If we look at that carefully, work done can be expressed as force times distance, and then regroup that, we get force times distance over time taken, and you'll recognize distance over time taken as speed. So power can be expressed as force times speed. That we'll remember in the formula P equals Fv, and we'll look at some of its immediate consequences now. First of all, it leads to an alternative definition which is more often used, and that is 1 watt is the power produced by a force of 1 newton acting on a body moving at 1 meter per second. So what in context would the P and the F and the V be? Usually we'd be talking about a vehicle with an engine which has a certain power, and that gives rise to attractive force. When you think of a car's engine, it expresses itself by exerting a force which accelerates the car. That's the attractive force. So if we use F for that force, it can be confusing. So it's often useful to use something like Ft or D. Show on the diagram what you use and you don't have to explain it. V is the speed of the vehicle, which may be constant or the maximum or just an instantaneous value. I'm using velocity rather loosely there because often velocity will be the term that's used. So long as the force and the speed, the velocity are in the same direction, you can talk about force times speed and that will be correct. Now, first example is to calculate the power developed by a car's engine which produces a driving force of 1000 newtons when travelling at a constant speed of 45 kilometers per hour. Now, these questions or these contexts are breeding grounds for problems which have units which are non-standard. No more so than here where we have 45 kilometers per hour. So our first task is to convert that into standard units. Let's look briefly first though at the force diagram. We're going to have a speed written on that arrow. We have a driving force of 1000 newtons, and for the car there'll be three other forces: the reaction, the weight and the resistance, which may or may not come into the problem in question. I've put them there for completeness. So let's turn this 45 kilometers per hour into meters per second. We've got 45,000 meters I should say, over 3,600 seconds. That represents 45 kilometers in 1 hour. So that you'll see quickly cancels down, and you've got dividing by 9, 4 on the bottom and 50 on the top. So it's 50 over 4, which is 12.5 meters per second. So that's our first task done, and we can put a 12.5 onto the diagram. At this point then we're able to use the P equals FTV formula to say that what we're going to get is 1000 newtons, and that's times the speed, which we've just worked out as 12.5. So there we are. That will be expressed in those terms. That repeats exactly what I've said and gives us a final answer of 12,500. That will be watts, but it's a big number, so we now move into the alternative unit, kilowatts, and say that it's 12.5 kilowatts. There's my answer to the question in context and with the unit. Now let's look at a second question. This time we have a mass and it's non-standard units, but it's explained for us. It's 1500 kilograms. The engine works at full power at 20 kilowatts. That will have to be converted into watts, and there's a constant resistance to motion of 600 newtons. So we need to find its acceleration when it's moving at a speed of 10 meters per second. It will be the power which gives us the driving force and hence the acceleration when we use the speed. So our first attempt to deal with this will be to look at the force diagram, where we've got the 1500 marked appropriately converted. We haven't got the 20 kilowatts on the diagram because we're going to use it, but we have got the 600 and we've got the driving force. So the tractive force Ft is going to come from the power, which is 20,000 in watts, and that will be divided by the speed. So the speed we're given is 10, so the end result is that the driving force is 2,000. So now we're able to put the 2,000 on the diagram, that Ft is 2,000, and we can use F equals ma in order to work out what the acceleration is. So there we have the 2,000, and using Newton's second law for mass times acceleration, we can say that 1,500, I'll put the right hand side first, 1,500 times the acceleration which we're trying to find will be the 2,000 minus the 600, which gives us an equation for the acceleration. So there we are, that's what I've just said, and the answer worked out comes out to 1400 over 1500, and that boils down to 0.933 to 3 significant figures. Again, I've put my full display in as much as I can be bothered to write. And so the acceleration in context, the answer to the question is that the acceleration is 0.933, and that's meters per second squared. Now, consistent units are important. I've mentioned it twice in what I've said here. Do take note that everything needs to be converted, otherwise you end up with answers which you really can't understand because the units don't make sense. A car has mass, it's the same one. What's the maximum speed of the car? Now this time we'll have to think about the force diagram to explain what's going on. Now if it's the maximum speed of the car, we can see that there'll be no acceleration. So there must be a force balance between the Ft and the 600. So this time essentially we're being told that the Ft is equal to 600. So if we know the force and we know the power, we can then get to the speed. So that will be our method. So at maximum speed, acceleration 0, there's no net force. So as p equals ftv, then what we'll get is that the velocity is the power divided by the tractive force, which we've got as 600. So it's 20,000 over 600, which gives us, when we work it out, 33.3 to 3 significant figures, and so the maximum speed is 33.3 meters per second. That type of problem is very standard, where you have to infer that the tractive force is equal to the resistances, and from that work from the power to what the speed is. Well, that ends the video on power, force and velocity. The next in the same series will be on motion in inclined planes. I hope to be with you later to explore that.